Today we're going to talk about work energy equation for rigid body. And if hopefully you still remember in chapter 4, we learned work energy equation for rigid body kinematics. And so it's very similar, but there's slightly difference between rigid body and particles. So today we're going to look at what's the equation, what's the work energy equation for rigid body. And but first, let's just take a quick review of what we did in chapter 4 for particle work energy equation. And you still remember the equation? The equation goes T2 plus V2 and equals to T1 plus V1 plus the work done from 1 to 2 from non-conservative forces. And T, these are kinetic energy, and potentials are these are potential energy. We use capital V, and this is work done from non-conservative forces. And the work done from conservative forces are already included in V1, V2. So for any conservative forces, we can write the work done from them by using potential energy, change of potential energies. Okay, then how would that look like for rigid body problems? And since now we have a rigid body, um, the size, the shape really matters, and the dimension is important. So let's write it down. For particle kinematics, kinetic energy, and can be written as 1/2 mv squared, right? That's in chapter 4. In this chapter, our kinetic energy have kinetic energy includes 1/2 mv squared. Here we're going to add p. Let's see if this is our rigid body. We have a g, that's the center mass. Also, we have the random point p. So the first term looks similar with chapter 4, 1/2 mvp squared. But in this chapter, we need to include two more terms. That is m vp times omega cross product rg slash p. We're not done yet. The kinetic energy has one more term. That's plus 1/2 ip omega squared. If you're interested in how we change from this simple equation to this more complicated equation, and there's a derivation on your textbook, feel free to look it up. And I don't want to spend a lot of time on that here. So I just give the equation here. So for in this for chapter 5, when you have rigid body, we're looking at three terms for kinetic energy T. And that point P can be any point on your rigid body. So VPs are the velocity at that point P you're choosing. So if we have other points, like for example, point A, and if we only know the velocity at point A, you cannot just use VA to replace the VP in this equation. It has to be the velocity at point P. And this omega, it's the angular velocity of the rigid body. And in chapter 2, we learned for a rigid body, there is only one angular acceleration and one angular speed or angular velocity. So this omega is angular velocity for the rigid body. And Rg slash P, Rg with respect to P, it's a precision vector pointing from P to G, G with its mass center, plus 1/2 IP omega squared. IP here, it's the moment inertia of point P. And quick review here, since if point P is not the mass center, and we can use the parallel axis theorem to find any moment inertia on the rigid body, right? That goes like any point on the rigid body defined by Ig plus mdAg squared. We learned that last week, this week. Okay, so this is the main difference in kinetic energy in this chapter. You will have two more terms in this just to calculate what is kinetic energy. However, if you don't like this equation, you think it's pretty long, you want to simplify this, we do have ways to simplify this equation. Just like the special cases we mentioned in 5A, and if we pick P, it's our mass center G, then how would we change this equation? If the point P is point G. Okay, can I call someone to answer this? Hey, Michael, can you tell me if our point P is the point G, the mass center, how can we simplify this equation for kinetic energy? Michael, are you there? Okay. How about Adam?
Hi, Dr. O. Would that drop your RG slash P to 0 and make that term 0?
Yes, correct. That's right. So if your point P is point G, this goes RG slash G. And there's no distance between that 2 points. Therefore, I'm going to drop the second term here. And under this case, let's call it case 1. Our kinetic energy is going to be 1/2 mvp squared plus 1/2 ip omega squared. It's simpler. Right. There's another case here. If the point you choose, point P, happens, the velocity at point P is 0. So if we have this case, how would we simplify our equation? Oh, what else? How about Luke? Can you hear me, Luke? Okay, then call. How about Harrison?
What's up, Dr. L?
So if we have this case too, how are we going to simplify the kinetic equation here? Kinetic energy.
T is going to equal 1/2 IPW squared.
Yes. So if we pick the point that happens at Vp equal to 0, then we can drop the first two terms, only have this third term left. So that can make your calculation even easier. Thank you.
Dr. L, what is the IA equation? What's the second term?
This one?
Yeah, DAG.
DAG, that's the distance between A and G.
And A is just some arbitrary point, or?
Yeah, it's the point you're trying to calculate what is the moment inertia.
Gotcha. Thank you.
Yeah, so we do have these two special cases we can use to simplify how we calculate kinetic energy. Okay, that's kinetic energy. That's KE. Next, we're going to talk about, since if you look at the work energy equation, we have kinetic energy, we have work or potential energy. Next, we're going to look at work. In chapter 2, we learn work. Work from position 1 to position 2. Can be written as 1 to 2 times force times ET ds. And if the force in this case has the unit vector, and we have integral from 1 to 2, just ft ds. Right, that's what we did in chapter 4. And in this chapter, the work done can be a little bit, can be more complex. So you will run into a problem like the work done from a force equal to integral 1 to 2 F E T ds. That's the work done from force. And also, we have a second term here to plus the work done from momentum. Momentum, the moment, sorry. The work done from moment, theta. The first term is the work done from the force. The second term is work done from the couple moment. And this is also called force couple system. And this is a more complex problem. And we're going to run into probably one example with work being divided by two parts, which is force and couple. So those are the main difference in rigid body problems that is different from what you learn in work energy in particle. Now let's look at an example. Okay. Now if we have a, let's see, we have a disk that is sitting on a slope. The slope has angles theta. The surface of the slope has friction coefficient mu k, and the disk can roll down the slope with no slip. And we know the distance from the initial position all the way to the bottom of the slope, it's L. Can we find out what's the speed of this disk after rolling to the bottom? So what are we given here? It's mass, radius, and then L. We need to find out what's the speed of G, the center mass. So G is here. G at the bottom. Let's see how can we use work energy equation to solve this problem. So let's first identify where is our position 1, position 2. So here, let's say this disk is released from rest. So here is their initial position, and the end position 2, going to be at the end of slope. Let's call this position 2. Now let's take a look at all the kinetic energy at position 1, position 2. Kinetic energy at position 1. What is kinetic energy at position 1? And since it's released, let's write it down. If it says release from rest, so which means at position 1, there's no speed. And let's go back to our equation here. For kinetic energy, this is a 4 equation, and these are two simplified equation. So if we just use case 1, we pick the mass center for our kinetic energy. And so at position 1, kinetic energy is going to be 1/2 mvp squared plus 1/2 ip omega squared. Since the system is released from rest, so there's no Vp and there's no omega. Your omega is angular speed. Therefore, at position 1, we don't have any kinetic energy. How about at position 2? What do we have? So we know at position 2, this disk definitely has some speed going on, right? And let's go back to the equation. It's going to have a speed at position 2, and it's going to have some angular velocity as well. So T2 at position 2 going to have both first term and second term. Here we have 1/2 mv2 squared plus 1/2 I g omega squared. It's omega 2. Now we're done with the kinetic energy, T1 and T2. Okay, now we can look at here. Let me do this. And some of you may have the question, since here we picked point G for kinetic energy, can we pick other points? Since here we have 2 different cases, right? Do we have any point that has velocity equal to 0 in this problem? Velocity equal to 0. So, ask someone to tell me, do we have a point that has zero velocity? Lee, can you tell me? Okay, how about Jacob Ryder?
Can you say that again, Dr. L?
Do we have a point we can find has zero velocity in this problem?
Would it be at the bottom?
Yeah, the
Right,
contact.
right as it hits the bottom? Or would it?
Let's call it C. Yes, this is a no-slip problem, right? So we know at a contact point, point C, Vc equal to 0. Yes, that's right. So if we go back to the kinetic energy here, that's our case too. Do we have a point that has zero velocity? In that case, we can simplify this to 1/2 IP omega squared. If we pick C, and we can still end up with T1, 1/2 IC omega squared. This is released from rest, so omega 1 is 0, so this is 0. And for T2, it's going to be 1/2 I. Here I need to use IC because I picked 1C times omega 2 square. And you may have question, how come this the kinetic energy at position 2 has different expression if we pick different points to analyze kinetic energy? And actually, you will see that this IC can be expressed by IG by using the parallel axis theorem. So you eventually will end up with the same expression for T2. There, no matter which point you pick, and you will end up with the same answer. Okay, that's about kinetic energy. Do we have any question here? Okay, let's move on to the next. After kinetic energy, let's look at what is the potential at position 1 and potential at position 2. So what are the potential energies we have? Since we know this disk has a mass, so we know at position 1, depends on how we set up our datum for zero potential. If we see at the beginning here, the initial position is our datum where V equals 0. And at this new position, and we're going to have some potential energy. We're going to have negative potential energy, right? Because we're going this changing below the zero potential. So at position 1, that's how we set up the datum zero potential. So that's 0. At position 2, and we're going to have 1, going to be mgh2, which is negative. And if this is h2. And that h2 can be expressed in terms of L, the distance it traveled, and the angle theta. So it can be written as negative mg L sine theta. So that's the potential energy at position 2. Okay, now we have T1, T2, V1, V2. So back to work energy equation. And we still need to deal with this term here, work done from unconservative energy, unconservative forces. So in this problem, since we have this no slip condition, that tells us there will be friction force at the contact surface, right? And then I want to ask you, what's the work done by the friction force in this point? So I can tell you, let's write it down. U and C 1, 2, 2. If we have just a box sliding from the top to the bottom on the same slope, it travels distance is L. If the friction force is FF, and the work done from this non-conservative force from 1 to 2 is going to be negative F times L. That's when we have just a box. That's the same what we did in chapter 4. And remember, the friction force work is always negative. But in this problem, we have a disk. It's rolling with no slip. So that would change how we calculate the non-conservative work. Since we have a no slip condition, friction is only acting at the contact point. And at a contact point, we know that's kind of the instant center, right? And at the contact point, Vc equals 0. And so at that contact point, there's no motion because Vc equals 0. And that means F, the work done from the friction force equals 0. No work. The work done from non-conservative forces from, in this case, would be the friction force is 0. So that's something it's a little bit tricky to understand. Is just remember this: if you have a disk rolling from a slope with no slip condition, and the work done from the friction force is 0. Okay, so far we have all the components for work energy equation. We can put them together, assemble them. T2 plus V2. T2 is 1/2 V2 squared plus 1/2 Ig omega 2 squared, and plus V2, that is plus negative mg L sine theta, and it's equal to T1 plus V1. Both T1 and V1 are 0, 0 plus 0, and plus the work done from non-conservative forces, which is 0 as well. There we go. Now we have the full work energy equation. And we can solve, if you look at this equation, the only unknown here is this is V2 and omega 2. But we only have one equation. We only have one equation, but two unknowns. We can use what we learned in chapter 2, kinematics, to build one more equation. Because this disk is a rigid body, right? If that is a rigid body, And there's a relationship between V2 and omega 2. V2, this is from chapter 2, equal to negative omega 2 times the radius of this disk. Remember that? Or you can write omega 2 equals to negative V2 over R. If you know the radius of and any point that you know velocity, you can calculate what's the angular velocity of the region. And now we should have two equations. This is our second equation. With two equations, you are able to solve two unknowns. We can find an expression for V2. So V2 is velocity of the disk at the bottom of the slope and then equal to positive negative square root 2gl sine theta over r squared plus IG.
Why is the omega 2 negative? Isn't it moving counterclockwise?
Sorry, see that again?
Why is the omega 2 negative? Isn't it moving counterclockwise?
Check this. Okay. Yep, it's rolling from position 1 to position 2. Yeah, it is positive. Because omega is counterclockwise, so omega should be positive.
Yes.
This comes from your book, page 106. So the original equation goes omega equals magnitude of a velocity over the position vector from A to C. In chapter 2. Okay. Now I can make this problem more complicated. What if I change this? What if this disk now is connected with a spring? So at the initial position, position 1, the spring is unstretched. So if we have this example here, now we add a spring to this problem, how would that change our potential energy and kinetic energy? So for position 1, T1, position 2, T2, V1, V2. For kinetic energy, if this is released from rest, just like similar as the previous example, and the kinetic energy at position 1 is going to be 0, and at position 2, it's the same, right? It's 1 half V2 squared plus 1 half I G omega squared. So that it's the same with what we did. And since we have a spring, so spring gonna change the potential energy. So if we set the initial point, it's it's a zero potential for gravitational force, gravitational potential energy. And the spring is unstretched at position 1. And we're going to have zero potential energy at position 1. But at position 2, we're going to have negative potential energy from gravity, just like what we did in the previous example. And also we're going to have the potential energy from the spring, from the stretching of the spring, if you can see that. And the potential energy from spring is 1/2 spring constant times L squared. L is how much it gets stretched. And here the sign here, that's one of the problems in your last exam. The work done from spring, the potential energy from spring, no matter if it is compressed or stretched, it's always positive. Okay. And so that's V1, V2, the potential energy at position 1, position 2. And for the friction force work done non-conservative force is going to be 0 as well if the disk is rolling with no slip. Yeah, see, if we can add a spring, that will make this problem a little bit complex. And I can also make this problem a little bit harder by, still have this slope, the spring, which is unstretched at position 1, this disk, and now this time we have how about this disk is connected with a box. Let's make this slope a little bit longer. Still has the same angle. If I have a problem like this, now we have multiple masses, right? We have, let's call this mass 1, this bar is mass 2, this box is mass 3. If the system is released from rest with no stretch on the spring, and what would change? I want you to think about that. T1, T2, V1, V2, U1. Non-conservative force work. Okay, if we have a problem like this, the kinetic energy at position 1 can still be 0 because everything is released from rest. The kinetic energy at position 2 is going to be the sum of kinetic energy from mass 1, mass 2, and mass 3. It's going to be longer. We have enough space to write down. Let's write that down. So T2 going to be 1/2 1 V2 squared plus 1/2 Ig omega 2 squared. So this is just for your mass 1. So we need to sum what is M2. So 1/2 M2 V2 squared plus 1/2 Ig2 omega 2 squared. This is for mass 2. And plus, what is the kinetic energy for the box? For the box, 1/2 3 V2 squared plus 1/2 Ig3 omega 2 squared. Here, let me make it a little different. The notation, since for different rigid body, for different masses, they're going to have different angular velocity. So omega here, this is omega for the first mass, omega for the second mass, omega for the third mass. Okay, this is how you find kinetic energy if you have multiple masses in the system. And of course, we can simplify this, right? For M1, it's going to look like this. But for M2, we know this bar, it's fixed between 1, 3. So there's no rotation. For this probably there's no rotation. And for the box, it has no rotation as well. And you get a simpler form for T2. Right? And that's how you get T2. And let's look at V1, V2. V1, then you have to identify where is your datum where potential energy equal to 0 for gravitation. Then you need to find out where's the mass center for each mass and to calculate their initial potential energy. Be M1 0 minus M2 GH2 minus 3 GH3. Depends what's the dimension of the box and the link, and you need to write the corresponding potential energy for each mass at V1 and at V2 as well. At V2, can we have all 3 objects can have potential energy? So we have negative 1 GH, let's call this 1 pi, minus 2 GH2 pi, minus 3 GH3 pi. That's potential energies. And don't forget, in the in the work energy equation, we also have this work done from non-conservative forces. So we need to consider of that. So we know non-conservative force, in this case, is only friction force. And we did in the example 1, if you have a disk rolling with no slip, and the work done from friction force can be 0. So for mass 1, the work done from friction is 0. And for mass 2 has no friction force, it's not contact with the surface, so that is 0 as well. But for mass 3, that's something we did in chapter 4, right? It's a block sliding down, and friction, the work done from friction can be the friction force times the distance it traveled. Call that L. And so you will have something for this non-conservative work in this example. So overall, let's go back. We start with a very simple example with just a disk rolling from a slope. And we did rigid body energy, work energy equation. And we add a little bit more complexity into the example by adding a spring, and that would change potential energy at position 2. And later on, we did is we add multiple masses in the problem. And then you need to consider for each mass, you need to consider their kinetic energy, including both the first term and second term, depends which one you pick. In this case, we pick the mass center for all the three masses. And something to pay attention is this is a mixed problem with a disk. There's no slip, and also we have a block just sliding down from the slope. Therefore, the work done from non-conservative forces have this friction force times L from the block sliding down from the slope. And this, so Anna has a question, why there's no spring force in V2 for the last problem? Anna, can you tell me which one you're talking about? Spring force. Oh, I think I know what you're talking about. Here, V2 was the new position for all three masses. Yes, here we should have potential energy from the spring. Thank you. It's 1/2 K L squared. All right, that's all for today. Does have any questions, comments?